I'm Tim Ventura from AmericanAntiGravity.com, and today we're joined by Dr. Ralph Merkle, Professor of Computer Science at Georgia Tech, a respected pioneer in nanotechnology development and the director of the Alcor Cryonics Foundation. Ralph has become a true celebrity in the futurism community through his pioneering work across a variety of emerging technology areas, and he's joining us today to speak about recent trends in cryonics and nanotechnology, and future applications for these breakthrough technologies in the aerospace industry. Well, Ralph, thanks again for joining us. And I guess let's start out with cryonics, which I would like to describe, I guess, for the layperson of the audience, is a bit like maybe the sleeper ship technology that we've seen in a ton of different Hollywood science fiction movies. But I guess the big difference would be that the Alcor implementation, at least, uses liquid nitrogen to completely stop life, as opposed to maybe the slow sleep state that you would see on TV. Is that accurate?
Well, yes, Alcor currently uses liquid nitrogen, and patients are kept at a temperature of 77 degrees Kelvin, so it's very cold at that temperature, and chemical reactions are effectively completely halted. So basically, a person who is at that temperature can stay unchanged, quite literally, for centuries.
Okay. Well, actually, that brings up an interesting question now, that there are some chemical reactions that very slowly proceed at those temperatures, right?
Well, actually, down at that temperature, although in theory you can have chemical reactions going on, you've gone below the glass transition point. So essentially the tissue is locked into a vitreous solid, which prevents all reactions. There's still some radiation damage. If you go through the calculations, you find that there's a bit of accumulated radiation and background radiation damage. Obviously, if you're in a stainless steel dewar, there is no photochemical damage. So basically, those processes are brought to a complete halt.
Okay, but in the science fiction application, all right, the one again, there are so many movies it's hard to list specifics, but I guess in that application, as they're traveling through space, they're probably going to be picking up a little bit more radiation in terms of cosmic rays, right? Do you think that?
Well, basically, if you're going through space, presumably you'd be using this for interstellar travel. I don't know if it would be as useful in interplanetary travel. Interplanetary travel takes a shorter period of time. But the kind of time frames you're talking on interstellar travel clearly would be helped greatly if you could have some sort of suspended animation. I think one of the issues floating around is that cryonics today is pretty much by definition an experimental protocol. And by that I mean the following. If you think about it, right now we'd like to determine whether or not cryonics works according to the standard established practices. And those established practices are to use clinical trials. In other words, if you want to find out whether some treatment works, you try it out and see. Well, the appropriate clinical trials to evaluate cryonics are very straightforward. You take subjects, N subjects, I don't know why it's always N, but it is always N, and you preserve them at the temperature of liquid nitrogen using the currently best available protocols. And then, and here's the part that people have a hard time grasping, you have to wait for future medical technology, because at the heart of cryonics is the assumption that medical technology, say 100 years from now, is going to be not simply an incremental or a modest improvement over present technology, but really it's going to be a revolutionary advance, a quantum leap in our medical capabilities. And this quantum leap in medical capabilities will lead to the ability to reverse even the kind of injury you see in today's cryonic suspensions. And as a consequence, we should be able at that point in time to restore people to good health. So we have a problem with the cryonics experimental protocol, which is often found when you're conducting clinical trials, which is before you complete the clinical trials, people ask you whether or not the procedure will work.
Yeah.
And this, of course, is well known in the case of, say, an AIDS patient who is trying a new and experimental procedure, but it's posed in a much more severe problem, or in a severe way, with cryonics, because obviously in the case of cryonics, we're awaiting the development of whole new medical technologies in order to reverse the process.
Well, it seems like there are some very different assumptions that would go into this in a space-bound environment rather than here on Earth. I mean, I guess there's almost this implicit assumption, right? Because of the reasons that people go into cryonics. In some cases, it's advanced age. In other cases, you've mentioned it could be disease like AIDS, where it's progressed to the point where future medical technology is a prerequisite for a number of reasons, not just reviving the person, right?
Well, yes, basically, if you look at the practice of cryonics today, people who go into cryonic suspension are legally dead, and that's a requirement imposed by the social and legal environment we exist in. And being legally dead is not considered a good indicator. That should be distinguished, of course, from dead by current medical criteria. You can be legally dead at a point in time when, in fact, you could be revived even by current medicine. That occurs, for example, when you have DNRs or do not resuscitate orders. And you can also be legally alive but have no real life at all in any significant sense of that term if you've had enough brain damage that the centers of the brain are effectively gone, but the body is still breathing.
Sure.
And we have to distinguish those from the definitions of life and death that are going to be used, say, 100 years from now, when indeed we expect that people who are gravely injured today and who would be considered legally dead by today's standards could in fact be restored to good health.
Oh, I see what you mean. So as the law progresses and as technology progresses, then people in this suspended state may legally progress from being dead to in a truly suspended state, I guess, in that sense.
Well, basically, if you think about it, 100, 200, 300 years ago, people were declared dead when they stopped breathing or when their heart stopped. And nowadays, of course, if you stop breathing, you can resuscitate people, and if your heart stops, you can call in the crash cart and apply techniques to restore the heartbeat. And as a consequence, we no longer consider those as reliable indicators of life or death. So as time has gone on and as medical technology has improved, we've seen that our criteria for death also change. And this, of course, raises the obvious question as to whether or not there's some sort of gold standard or whether there's some actual definition of death which is independent of technology. And I think the answer is yes. I think basically as time goes by, we find that we should have a medical technology based on a mature nanotechnology which would let us reverse all the damage that occurs if, in principle, it can be reversed. So you start asking yourself rather fundamental questions of what kind of injuries can, in principle, be reversed. And when you ask that question, you find that, in principle, almost any damage which lets you identify the structure can, in fact, be reversed. So today, if your heart stops, that's a functional change. The heart can be started up again. If the cells in your body stop metabolizing, today we are unable to reverse that injury. But in the future, if a cell is not metabolizing or if the cell's energy levels have fallen too low, then that injury could be reversed by a sufficiently advanced medical technology, and as a consequence, in principle, a person would not be dead and therefore should be in a state which could be restored to full health.
Sure, sure. Well, I guess the fundamental difference, and again, to go back to the spacebound environment, the idea in terms of transport, I guess one of the thoughts there, I mean, obviously, since this technology on Earth is waiting for more advanced technologies to come along to revive the person, I guess one of the prerequisites would be, having to hold off for this type of cryotransport until those new technologies can actually be packaged onto a spacecraft to revive the person automatically, right?
Well, pretty clearly, I think this kind of experimental procedure is not one that you would want to apply to someone who is healthy. So, for example, an astronaut would not wish to be suspended or cryopreserved with current technology because we have no experimental feedback that tells us that this is going to work.
Yeah.
We think it might work, and we think that it's worthwhile, obviously, if you're facing imminent death, then it's better to be cryopreserved than not, because you have some probability of success, I think rather a good probability of success. But that probability of success is not perfect, and as a consequence, you'd like to avoid using that on astronauts as a routine measure.
Sure. Well, I think one of the things that's kind of gotten me excited about cryonics again is, having read through the Alcor website, one of the things that I noticed were a lot of very recent advances in the vitrification process. And it seems like, I guess I would hold this view also, that a lot of people in the audience would probably believe that when you get frozen, your cells explode, and therefore, very advanced nanotech may be able to repair this, but that it's not very likely in the near future. But it looks like that's changing, right?
Well, the image of sort of cells bursting from ice inside has always been incorrect. It turns out that when you cool in the absence of cryoprotectants, then you get ice formation externally to cells, and the cells themselves are dehydrated. If you use cryoprotectants and ice blockers, and in fact, Alcor has been using cryoprotectants for decades now and has recently adopted a new set of cryoprotectants and ice blockers that allow you to vitrify. In other words, these new cryoprotectants and ice blockers suppress ice formation entirely so that, in fact, you can cool a tissue and not form ice. This is a process known as vitrification. And obviously that eliminates the concerns about ice damage, which we find to be a very good thing. We're very pleased with that.
Yeah, it seems like a tremendous. I mean, I'd always considered that to be the largest challenge to the first step, which is getting the person on ice, figuratively speaking, and then that next step, I guess, technology can evolve towards in the future.
Well, certainly with the advent of vitrification, a lot of people have said, oh, in that case, the level of damage that's caused by the cryopreservation process has been drastically reduced, and therefore they're now a lot more interested in the process. I think it really has gotten a lot of attention. A lot of people have said, oh my, this looks like it might actually work. Good heavens.
Yeah, I'm definitely one of those people. Well, I'm wondering if some of these recent advances, I'm wondering if human cryotransport, I guess via the Alcor model, has been the beneficiary of cell storage techniques from other fields, such as the storage of reproductive cells for artificial insemination.
Well, certainly the research on the research on vitrification has been carried out by a number of laboratories at this point. The person who's been working on it for the longest, I think, was working on vitrification of kidneys for the Red Cross for many, many years. And the techniques that he's used are published, and Alcor is using those techniques to provide vitrification.
Okay. Well, speaking of which, since you mentioned kidneys, one of the thoughts that had occurred, and I don't know if this is something Alcor is considered or not, but for the neurotransport, I'm not sure if that's the technical name, but where they preserve only the person's head, I believe the cost for that is still around $100,000, right?
Okay, well, basically the cost structure at this point is $150,000 for preservation of the entire body. And if you wish to preserve the brain and are concerned primarily about brain function, then you have neuropreservation, which costs $80,000. I should mention that these are typically paid for with life insurance, so the actual payments by the individual are quite affordable.
Sure.
Then basically the neuropreservation technology preserves the entire head, because obviously if you remove the brain from the skull, you're going to cause damage at that point, which you want to avoid.
Yeah.
And the reason that neuropreservation is used, of course, is that we expect that the medical technology which will be required to reverse the cryopreservation injury is going to be able to replace any missing or damaged tissue, with the obvious exception of the human brain. The human brain has to be restored, because if you don't restore the human brain, if you try replacing the brain, that doesn't work very well. You lose all of the information that makes us who we are.
Well, has Alcor ever considered the model of organ donation as an offset? I mean, the life insurance option definitely seems like that.
Well, legally, we're using the Uniform Anatomical Gift Act, and basically the forms that you sign say, yes, you're making an anatomical donation to Alcor. So in some sense, we are using the ability to donate organs in order to facilitate the legal process.
Okay. Interesting. Well, so in terms of building new bodies, that almost seems like it adds in another hard time limit. And I guess that would take advances in cloning to reach that. But in terms of just transporting the brain and the head, then you have to build a new body around it. I'm wondering, what kind of timeline you think that might add to how soon a person could be revived?
Well, basically, the kind of time frame required for the development of molecular nanotechnology, which would give us an ability to arrange and rearrange molecular structure in most of the ways permitted by physical law. Time frames on that are on the order of decades, but not on the order of centuries. So we would be reasonable to assume that sometime within the next several decades, we would have a technology in place that would let us rebuild tissue and replace any missing or damaged tissues.
Yeah.
And of course, it's not entirely clear that we'll be using the biological model for the replacement of tissue. The biological model involves, for example, as you mentioned, cloning or tissue engineering of some type. We might also simply use some constructive technique to build the appropriate tissues, or indeed we might build an artificial body. In other words, you might build a body that was functionally equivalent, but which actually didn't follow the details of biological systems, but was more of a bionic body. So there are a lot of options at that point, and basically I am content to let the future sort out which of the numerous possibilities proves to be most cost-effective and most desirable.
Well, it's an excellent point, and I think Ray Kurzweil has touched on this also, that a lot of people would look at having a machine body, or for that matter, even uploading the mind itself, uploading the details of the brain into another medium. A lot of people would look at that as a step down, as being something less than human, but that's just our perception at the moment. In fact, it may be something far more than human. So,
well, obviously there are a lot of possibilities, and this begins to get into a variety of philosophical issues. I think it's sufficient to point out that one could expect a technology that could restore people in their full biological, current biologically accepted form, and that is obviously sufficient. And then if some other technology proves to be desirable and people decide after thinking about it for a suitable period of time that it's a good idea, then those would also be available.
Sure, sure. Well, that takes me actually into my nanotech questions. And I guess the good crossover is that cryonics, at least from what I've read and from what you've said, in a way almost seems to require some degree of nanotechnology.
Well, I think that's true. Obviously, you're looking at quantum leaps in medical technology, and the kind of quantum leap we're looking at is going to require the ability to really go in at the molecular and the cellular level to deal with the fundamental damage that's been caused and to reverse that damage. And I think it really is only realistic to do that if you have a full-blown molecular nanotechnology to enable that kind of repair.
Yeah, yeah.
So yeah, basically, cryonics is a bet that medical nanotechnology is actually going to be developed in more or less the form we think is feasible.
Okay. Well, in terms of nanotechnology, I had been following this almost religiously, from the late 90s into the early thousands. And I really had the impression, at least in terms of the media, in terms of the coverage and the publicity and the hype that it was getting, that it seemed like it was really hurt by the dot-com bust. Do you think that's the case, or was it just
Well,
maybe...
certainly the dot-com bust reduced the amount of money available for a variety of R&D activities. So in general, the dot-com bust was not a good thing for nanotechnology, but I think the level of interest in nanotechnology has been going up and is fairly widespread at this point.
Yeah, no, it definitely does. It is progressing, and nanotech is actually a buzzword these days. And I guess the next question is that because nanotech is becoming a buzzword, it seems like there are an emerging number of commercial products claiming to be nanotech. Nowadays, there's lipstick, different types of fabrics, all sorts of things. And
well, yes, that is a problem.
Well, I'm wondering, is it fair to reclassify everything using nanoscale molecules into the nanotech category, or is there a hard and fast definition that cuts through some of that marketing hype?
Well, basically, the kind of nanotechnology which I think is interesting and which was originally defined by Drexler back many years ago is the kind of nanotechnology that is now more specifically called molecular nanotechnology or molecular manufacturing. And that really gets back to a talk by Richard Feynman, the Nobel Prize-winning physicist, who in 1959 proposed that we should be able to develop a manufacturing technology that would let us arrange the atoms in most of the ways consistent with physical law. And I think that definition and that image of nanotechnology is the one that really provides all of the high payoff long-term objectives and goals. The use of nanotechnology as a buzzword, of course, has become so extensive that, as you say, any kind of research is now labeled nanotechnology research, and it's not entirely clear that that broad usage is useful in any particular sense.
Yeah, it does really kind of go to that marketing aspect, and the cosmetics part for me, that was the straw that broke the camel's back. But well, in terms of, I guess, Drexler and Feynman, it seems like there's a little bit of competition there, in the community of people who are fans and following nanotech trends, for which one, I guess, is probably the father of nanotech. Now, personally, I think Drexler really qualifies more in that area. Feynman made a casual observation about nature, but he didn't have the focused, refined concept that Drexler introduced. But I'm
Well, I
wondering.
think you're correct. I think basically Feynman's very visionary talk in 1959 was something that we can look back on and be amazed that he actually considered the possibility at all. But it is certainly the case that Drexler's work, and I think the work of others subsequently, has gone into much more detail as to what such molecular manufacturing systems might look like, what the basic principles are, what the limitations are, how they might actually function. And indeed, I think it was Drexler who provided a synthesis of the work of both Feynman and von Neumann. You'll recall it. Von Neumann was talking about manufacturing systems, universal constructors, manufacturing systems that could build other manufacturing systems and things like that.
Yeah. Well, do you think, historically speaking, Drexler will end up being kind of considered the true father of nanotech then, or do you think?
Well, I think that's the case. You have to look at this and say what's going to be happening and what are the ultimate winners going to be. I think basically one of the core concepts that Drexler has talked about is positional assembly and the use of the concept of positional assembly down at the molecular scale. So I think as that technology gradually comes to fruition, as people find that they can indeed build molecular structures by using positional devices, whether it be a scanning probe microscope today or some descendant of the scanning probe microscope in the future, then I think we'll find that Drexler will increasingly be credited with that because he basically described how that would work and what the possibilities were.
Now, it's interesting. I've heard, I guess, the rumor mill is churning out rumors saying that Drexler is kind of moving back a little bit from the limelight in the nanotech industry, and that, I guess, the critics are suggesting that maybe this is the end of the creative vision, the beginning of some bureaucracy for nanotech. But do you think this is the case, and does that mean that maybe this is really emerging as a real industry, or is the field just getting complicated by a lot of hangers-on who just kind of want to associate themselves with the latest fad?
Well, basically, I think that there is a lot of funding for something called nanotechnology, and obviously people who want to pursue funding or who are advertising commercial products, whether it be suntan lotions or whether it be something else, basically the use of the term nanotechnology has become so widespread that really the term itself is no longer particularly useful unless you qualify it. So, for example, in the discussion we're having, obviously we're talking about molecular nanotechnology, which gets back to the kind of statements that Feynman and Drexler have made. The broader concept of nanotechnology is encompassing anything where some critical dimension is less than a nanometer, less than 100 nanometers, really is so broad at this point that it's not entirely useful.
Yeah, it's an excellent point. It's almost, Bill Joy had written at length about the gray goo, right? I think Michael Crichton addressed that also in one of his books.
Mm-hmm.
The gray goo that gobbles up the entire planet. But in terms of sciences, nanotech benefits from this convergence of trends in material science, computing, communications and optics, medicine, biology, and several other fields of study. And in a way, the gray goo almost seems like it's consuming scientific textbooks as well. The definition of nanotech itself is encompassing everything. So,
Yeah, it really is an area where you have to be careful about what it is you mean when you say nanotechnology.
well, what do you think a good degree program is for younger people interested in a career in nanotech?
Well, that's something people ask. It's on my nanotechnology page is one of the most frequently asked questions is, what should I study to get into the area of nanotechnology? And really there's no good answer to that other than it probably would be very useful to learn molecular mechanics, which is a fundamental molecular modeling technique which allows you to understand how atoms and molecules can interact with each other. Understand basic chemistry, because if you're going to talk about manufacturing out of atoms and you're rearranging atoms, that sounds an awful lot like chemistry.
Sure.
And beyond that, there are a number of different areas that can be pursued and which should be pursued, I think, depending on your particular proclivities, your abilities, your desires, your interests, and an in-depth understanding of almost any one of those areas would be something that could be used to contribute to the development of nanotechnology.
I'm wondering if there are any degree areas that may not apply in the future. And I guess the thought that comes to mind is in the early days of computers, I know a lot of fellows were pursuing writing in assembly language. Back then it seemed like a good idea, but nowadays, it's so bare to the metal that nobody uses it. Do you think there's anything that just may end up being just archaic and not used in terms of
Well, it's
nanotech?
hard to say which way the technology is going to go and which particular bits of information will be useful. On the other hand, assembly language is something, even if you don't use it, knowing how the machine works is always a useful bit of knowledge and helps you understand at a conceptual level what's going on. So even if we do find ourselves in the future using some sort of set of rules or design rules or techniques to simplify the process and simplify the chemistry, understanding the basic issues of what goes on with atoms and molecules is going to remain useful for, I think, a very long time. The world is made out of atoms and molecules, and understanding how they interact and how they can be used to build more complex structures is going to remain useful knowledge for some time.
Absolutely. Yeah, I guess the thought that had occurred was maybe, after nanotech matures a bit, some of the building blocks themselves would become larger components. Instead of having a collection of atoms and molecules, it may be the assembler, right?
Well, I think there will be sort of simplifications in the design process and the manufacturing process, and certainly one could envision a manufacturing process that uses, say, a dozen or 24 basic building blocks, where the basic building blocks have hundreds or thousands or tens of thousands of atoms in them, and the assembly of those basic building blocks is then what's primarily done and what allows people to design and build more complex structures. Certainly you have that kind of layered control of complexity in computer science where you can have successive levels of abstraction which allow you to deal with very complex structures and yet maintain the understandability of the structure and understandability of the software in a way which lets you deal with it intelligently and reasonably.
Well, the other part is powering these devices. And I understand that they've even been playing around a little bit with ATP, the standard cell fuel, for lack of a better word. But
Well, certainly there are a lot of possibilities for power, ATP, or other chemical fuels. Obviously, if you have a device which is operating inside the body, you might want to use glucose and oxygen. So a glucose and oxygen fuel cell might be just the ticket in terms of that kind of medical device. If you're talking about a device which sits on a desktop, then power could come from an electric power plug. Basically, you take standard electricity and use that for the power of the device that's a desktop application. And of course, there are other sources of power that are commonly used. Batteries are often used for portable devices, and we use chemical fuels for automobiles, so certain kinds of mobile devices would use that kind of fuel or could use that kind of fuel. There are a number of fuel sources, and obviously the fuel source would depend on the particular application.
yeah, yeah. Well, I'd wondered about RF for something like, for some reason, JSTOR Hall's nanotech fog. That the foglets have always intrigued me, and I thought about perhaps a specific frequency of RF that might hit an antenna on something like that, providing, yeah, it wouldn't be complex power, but maybe something simplistic, I guess.
Well, that's certainly one of the possibilities. I think the current experimental work in that area is not as extensive as with some other kinds of power technology, but certainly broadcasting power by using radio frequencies has been done.
Yeah.
So it's one of the possibilities.
Well, we're almost out of time today, Ralph, but I sincerely appreciate your joining us. And
Well, it's certainly been my pleasure.
yeah, well, to be honest, it is an honor and a privilege to have interviewed you. You've had such a great depth and breadth in this area that I'm glad to be able to finally add, some of your knowledge and help put it out there for our audience.
Well, thank you.
Well, thanks again and have a nice evening.
Okay, thank you.